Okay, thank you once again. This will be our fourth lecture, and this will be our last. So my discussion will be much more not in our normal space. We are going to discuss in the Hilbert space. So if we reduce things in the Hilbert space, things will be easier. So as we have the following very important result, that's thanks to recess representation. Let H be a real Hilbert space. A complete inner product space, a complete normative space where the norm induced by the inner product. So let's have this. Let me, as to start this, let me discuss things which I discussed before when it comes to the Hilbert space case. When it comes to the Hilbert space case. So what makes things simple in Hilbert space case is just to remind you, but it's just to remind and to recall it. That's this very important concept. If H is a Hilbert space, for every I, an element of the bounded, this one, for any bounded linear functional on H, there exists in the Hilbert space case, there exists a unique element in H. This element depends on the functional F. This, you can find a unique element in H such that phi of x is equals to, or that's this one, right? What we know is this if this is H star, right? This is H star of X. This is from H star cross H. This is the one which we discussed, the bilinear form between the dual space and H. This, which is equals to, obviously, in a simple form, this one. You can find a unique element in H, say that this can be represented as this inner product. This is inner product in H. This is the inner product. So any linear functional can be represented as inner product, Anyways, in addition to this, the norm of here, for this choice of unique d phi, the norm of this operator is equal to the norm of this element in H. Additionally, we have this one. Because of this, H, the dual space of a Hilbert space can be identified as with H itself. With this relation, so the dual of the Hilbert space can be identified as the Hilbert space. And the linear functionals are, bounded linear functionals are linear functionals on H are simply inner products. The inner products. So the boundary linear functionals as this. So meaning that this is to mean that is equals to Z. Where Z an element of H. H is the whole space. The whole space. So this will also indirectly tell us that Hilbert space is reflexive. So this makes it a very simple case so that the since we have reflexivity and each boundary linear functional can be represented as inner product, So because of this, let me discuss the following thing, which in the view of my discussion, which I discussed in the last three discussions. Let H bar be Hilbert space. And let's have this. F from H bar infinite on H bar be this the functions and A be an element of boundary linear operator from H to H bar. So simply subdifferential of f at x is the set of all z in H now. Say that it's just like this. Because of, and if we have this, how about the dual? F star is from H. So the dual space of H is represented as H itself. So this is this one. F star of any point Z is the supremum of Zx minus f of x. This is the inner product. This is the inner product over x in H. So how about this sum? So if we have this, the infimum of the primal problem, the infimum, which is this is a primal problem. This is equals to, when it comes to the dual problem, it will be like this. Minus of minus S star of y minus G star of y, where y what? Y is an element of H bar. So H bar star is H bar itself. So when you This is how it will be reduced when the space is in the Hilbert space case. When the space is in the Hilbert space case. So having this in mind, now I can go to proximal operator. So what is proximal operator? Proximal operator is famous when discussed in the Hilbert space case. Let H be a real Hilbert space. And given a function f from H to this space, to this set, then what is Moreau-Yasuda regularization? The 4. If we have scaling lambda greater than 0 and a single element in H, the Moreau-Yasuda regularization. With parameter lambda x denoted by this, the Moreau-Yasuda regularization parameter, the Moreau-Yasuda regularization of f with parameter lambda x is denoted by this one usually is a real, it also maps from this to this one and is given by this, the Moreau-Yasuda regularization at a point y is f of y plus 1 over 2 lambda minus x minus y, norm of x minus y, the whole square. So the Moreau-Yasuda regularization of a function f with parameter lambda x is this mapping. So if f is convex function, norm is strongly convex, so it will be strictly convex. So strictly convex. So it means that we have a unique solution. If f is proper, let's see like this: convex and lower semicontinuous, then you see the regularization of f with parameter lambda x has a unique minimizer. So if f is convex, norm is strictly convex. So convex plus strictly convex gives us strictly convex. So this will have a unique solution. This implies that the argument of Moreau-Yasuda regularization y in H is singleton. As a unique solution. So, so we can have a mapping, a real valued mapping using Moreau-Yasuda regularization. So that real valued mapping is called proximal operator. Proximal operator. Let f from H to R plus infinite be convex, proper, and lower semicontinuous function. Then the proximal operator of the function f with scaling lambda. For lambda greater than 0, the proximal operator of f with scaling lambda. Lambda is denoted by this one. The proximal operator of the function f with scaling lambda is denoted by this one. This one, and this operator, the proximal operator of a function f with scaling lambda is a self-mapping. It maps a point in H into H given by, it is just argument of the Moreau-Yasuda regularization parameter. So this is the proximal, this is equal to given by the proximal of at a point y, at a point x is the argument of the Moreau-Yasuda regularization. Which means that this is the argument of f of y plus 1 over 2 lambda of norm of x minus y, the whole square, y runs in H. This is it. This is called the proximal operator. This is called the proximal operator. So proximal operator has a lot of properties so that it will help us to study optimization problems as a fixed point problems. It's one property, it is proximal operator is firmly non-expansive operator. And it means that it is also non-expansive mapping. It's also a non-expansive mapping. So how about if we consider the indicator function in place of f, the indicator function, what will be the proximal operator? If C is closed convex subset of H and G, F is equal to this one. Then what is the proximal of this one? If f is the indicator function, what will be the proximal operator? If it is an indicator function, the proximal operator is the argument of f of x, that is the indicator function. Okay, it doesn't matter. F of x 1 over 2 lambda of x minus y, the whole square, y in x. So this is argument of, so it's just considering in space T only. If it is in space T, it is one. This is the argument of simply this one. Or I don't need to state it anyways. This is argument of so what does it mean? So this is this H will be C in C. This will be in C. So it's just finding the argument over C. We do not need to find the whole space. So this means that it is just finding a point in C very close to X. Among the points in C, the point which is closest to X. If we have C, the proximal operator of this one is, if this is closed, the smallest distance. It's the smallest distance. So this means that if F is a proximal operator, the indicator function, the proximal operator will be reduced to the projection of a point on a set C, So this means that proximal operator is the natural generalization of projection operator. That is a natural generalization of proximal operator on the whole space X. It's believed to be this one. It's believed to be this one. So, what is the relation of the proximal operator with a subgradient, with a subdifferential operator? This is a point in C. This is just finding the point in C. This is the point Z naught. This is the point Z naught. Or if this is a proper convex function, the proximal of f at the point x is y, if and only if x minus y over lambda is an element of the subdifferential of y. Subdifferential of y. This is a connection between proximal and subdifferential. If the proximal operator of at a point x is simply Actually, the differential operator has a lot of properties. The differential operator is maximal monotone operator. So we can study it as a resolvent operator. As a resolvent operator. This as a resolvent. We can discuss it as a resolvent. So since this is maximal monotone operator. So we can have also this connection. We can have also this connection. So what will this tell us? This implies that X bar is minimizer of F if and only if 0 is an element of the subdifferential of F. This is from the first order condition, right? X bar. 0 is a subdifferential of X bar. Is an element of the subdifferential. Meaning that by this one, X bar, right? Anyways. This is what it means. Anyways, this means that 0 is an element of the subdifferential, meaning that X bar minus X bar is an element of the subdifferential of X bar. If and only means that the proximal of X bar is X bar. The proximal of X bar is X bar. So this implies that X bar is a minimizer of F if it is a fixed point of the proximal operator. If X bar is a fixed point. Of the proximal operator. If it is the fixed point of the proximal operator, this is very important. So in the non-smooth optimization, so finding the minimizer of the non-smooth minimizer is just finding the fixed point of the proximal operator. So this is one concept, so that fixed optimization problems can be studied as the fixed point problems, because several optimization problems involve operators with a special property, maybe free real and expansive, non-expansive, like proximal operator, gradient operator. These forms have special property as an operator. Those can be studied as fixed point problem. One operator which is discussed in the view of optimization is proximal operator. And proximal operator has a connection with a fixed point problem of this one. So, so it can be studied as a fixed point problem. So I would like to state this again. The proper convex lower semi-continuous function. Then what is very interesting is the proximal of f at x, if lambda is not here, meaning that the proximal operator of f with scaling lambda, with scaling 1 of f, is simply written as this. If lambda is 1, write this. If it is written this, means that the scaling lambda is 1. the proximal of f with scaling 1 of x plus the proximal of f star with scaling lambda of x is x. Very interesting. Maybe I don't know where we will use it, but it's very beautiful, I think. Proximal of f at x is the proximal of the dual of f of x is equals to x. This is simple. If we let the proximal of if we let proximal of x is z by one of our theorems there, x minus z, and is an element of the subdifferential of f at z. Again, I'll come back to our Fenchel conjugate. If x minus z, if this is a linear functional, if x minus z is an element of the subdifferential of f, meaning that z is an element of the subdifferential of f star of this. X star is in the normal space, is a subdifferential of f at x if and only if x is an element of the self-differential of f star of x star, provided that f is lower semi-continuous and reflexive. So Hilbert space is reflexive, and we have lower semi-continuous. So due to this one, we can connect it here. If it is finite dimensional in Hilbert space, complete inner product space, even if it is rather than discussing in normal space, if it is also Banach space, it's okay. If it is Hilbert space, things are very simple than considering in normal space. This means that I can rewrite it this way. Right, this is D. So again, here also, if this happens, this happens. So the proximal of f star of x is x minus c. Where is this? So replacing we have z here. The proximal of f star of x is x. If you replace c. So regarding proximal, I would like to state only the following. Then I will come to the numerical result, which I found it very interesting is this one. If we have This is a relation between proximal operator of a function and proximal operator of the Fenchel conjugate. We can make also this one. Doesn't matter. It doesn't matter because if we make his conjugate, we make again here another conjugate, the conjugate of conjugate. This is a, right? If you make here star also doesn't matter. Or if you make star here and if you don't have a star, it also doesn't matter because star of star is F itself. So this will help us. This will help us to find the proximal operator of the Fenchel conjugate of a function. Fenchel conjugate of a function having the proximal operator of a point x. We have this. We can kind of find this one. We don't need to compute another proximal using the formula. Now, just to finish, I will like to state around three numerical results of optimization algorithms. Very classical ones. Very classical ones. The first one is the maybe we can proximal point algorithm. Yes, let's start from this. EPA. So we consider the minimization problem f of x, find, and consider finding x bar in H such that the point x bar is a solution of the infimum, or it doesn't matter, the minimum in here. So if where f is from this to this is a non-smooth optimization. Is proper convex and lower semi-continuous function. So this is a non-smooth optimization. So we don't need differentiability here. We don't need differentiability here. So we know that, noting that this one, I don't need to write it. X is a minimizer of f. If it is a minimizer of f, it is the fixed point of the proximal operator. It is a fixed point of the proximal operator. So the PPD is proximal point algorithm is this one. The PPA is let x1 be the initial guess or initial guess, and lambda n be the sequence of positive real numbers. With this one. This parameter should satisfy this. Then the sequence generated by the sequence xn generated by the iterative scheme. So having this concept, the sequence generated by this one weakly converges to a point x bar, an element of argument of f. So if we have a non-smooth optimization, this one, and if you have a solution x bar, an element of x, right? So the sequence, so we can discuss about proximal here. So the solution of, if this is the solution of this one, is the fixed point of the proximal operator. So if we iterate, if you give it initial guess x1 as a solution, as a possible solution, and you don't know how far you are, the solution may be here. You give it the initial guess, so iteration it will approximate this point to the solution. So the sequence generator for this parameter lambda, for this scales of the proximal operator, the sequence x generated by this one weakly converges to this one. Actually, this is famous. This is discussed weak and strong convergences and proximal point algorithms, and its versions are very famous by Rockefeller, as a Professor Rockefeller. There's many discussions of this one. The second discussion will be forward-backward algorithm. So the problem is this one. Could be proper, convex, and lower semi-continuous function. This is smooth, and we have G to be non-smooth. This is proper, convex, lower semi-continuous, and Fenchel differentiable. with L Lipschitz So this optimization problem is discussed under this condition. F is non-smooth. F is proper convex law or semi-continuous function. G is proper convex law or semi-continuous function and Fenchel differentiable function. But the Fenchel gradient is L Lipschitz. Okay, it's a Lipschitz continuous operator. With this condition, we discussed the forward backward algorithm we discussed. So how it is developed, how this algorithm is developed. So under this condition, let's assume that H, it is a minimizer of this one. By first order condition, we have that 0 is an element of. So assuming that, I need one extra assumption. We need to have this interior of domain of F intersection domain of G. There should be this condition. Otherwise, I cannot have this. I cannot have this. Because what I can say is by first order, because this will not guarantee that this is a subset of this one. So there should be equality, right? Otherwise, the reverse should hold. But this is not the subset of this one. This is a subset of this one under that condition. So then that we need to have this one to have this one. So meaning that we can have this. We can have this. This should make the difference. So there must be an element in here. D plus this gradient should give us 0, right? There is some D, an element of this one, so some W, an element of this one. W can be written as V minus X bar over lambda for some Z, and you can fix any scaling lambda. And this, your choice of scaling lambda is called regularization parameter. Regularization parameter. You can write it this way. So this implies that from this one, the proximal of a function f with scaling lambda of Z is X bar, and Z is equals to X bar plus lambda as a gradient of G X bar. We can have this. From this, we have this. By one of our theorem, we can have this. So therefore, X bar can be written as this form. The solution of the optimization problem can be written as the proximal of Z, but this is this one. So the solution of this optimization problem, X bar, has this kind of property, meaning that X bar is a fixed point of this operator. So the solution of this optimization can be studied as a fixed point of this problem. So let's have the mapping. So it's just a matter of defining this. Let's have this. So finding the solution of that optimization is just as a problem of finding the fixed point problem of this. It might be, yeah, it is among the fixed points. If among the fixed points, it will be its solution, right? So, but what we know is the solution of that one is a fixed point of this operator. The fixed point of this operator. And you can approximate it this way. Where Xn is this one, where it says that it can be studied as an approximation of the iterative scheme of this one, where alpha n is relaxation parameter. We call it relaxation parameter. And if alpha n is this is over relaxation, It's assumed to be this is over relaxation. If alpha n is this one, it is under relaxation. So having this one, the forward backward algorithm is given by this. Forward backward algorithm. Let lambda is fixed between this one, where L is the Lipschitz coefficient of the gradient, the Fenchel gradient. If lambda is this one and 0 is less than or equals to alpha n is 1, that is under relaxation. That's this one. And x1, this is the initial guess. Initial point or the starting point. You can say it's starting point. Okay, you give it an initial guess, then for a sequence xn generated by Zn is equals to xn plus lambda of the gradient of g at xn plus 1 is equals to xn. Now we use this 1 minus alpha n of xn plus alpha n of the proximal of lambda n of f of Zn. The sequence generated by this iterative scheme weakly converges to the solution of that. Weakly converges to the solution of that. This is forward backward algorithm. It converges to this. It has its own proof, which is very long, which is a very long proof. So this has a lot of problem, a lot of application. One application is the minimizer of this problem in L1 not. In signal processing, image recovery kind of optimization problems can have an optimization problem where this is smooth and this is non-smooth. Lazo problem has kind of this where one can be treated as smooth and the other one is non-smooth, and this is one application. It can also solve this one. it can also solve this problem. Actually, this smooth and smooth problem, signal processing, image recovery, all these things have this form, and these all things can be discussed or solved using this forward-backward algorithm. The extended versions of this algorithm are recently given. We have many algorithms which are improved versions of this algorithm. It is weakly, so I think there is also a weak convergence, which is, this was a classical one, was the oldest one. So many has tried to improve this algorithm in terms of, not only in terms of also giving it a faster convergence, and also improving it to strong convergence is also one result. So many has given a lot of results on this one. This is L1 norm. Let's make it like this. Yeah. Let's make it L1 norm. The last one is it is problem of this one again. But in this case, the two functions are non-smooth. Here, in this case, the two functions are non-smooth here. This implies that the self-differential of G at X bar. Again, just want to use this. So meaning that this implies that, again, the sum differential of G at X bar for some ZH, the lambda is strictly greater than 0, which we call it regularization parameter. You can give it any you can give it any positive lambda. So this implies that Z minus X bar is an element of lambda times the self-differential of f at X bar, and twice of X bar minus Z minus X. We can write it this way. Is an element of the self-differential. And with this is right? This is what we said last time. That's why I'm jumping one step. I was using one of my property before. We have this, and the proximal of lambda g of x bar minus z is equals to, this is x bar, sorry, x bar. Z is equals to I don't need to write it anyway. So the next which I'm replacing is because of this form. I'm not writing this way because I don't need it is I don't think it's important, but why I'm writing this is this one. In place of x bar we have okay, yeah, x bar minus z. X bar is proximal, right? Proximal, twice of proximal of f at z minus z. Place of x, I'm replacing this one. And x bar, I can use this. Lambda g of 2 of proximal of lambda f of x minus x minus the proximal of lambda f of x. So it can also be studied, x can be studied as kind of a problem of this way, this form. If x is fixed, meaning that these are equal, right? Actually, we can manipulate. This is equals to 0. The proximal of lambda f minus x is an element of the subdifferential of g at x bar. It is fixed. Anyways, having this one, the Douglas Rashford algorithm is giving that the initial point should be Z1, okay? So that's the proximal of lambda F of Zn plus 1 is equals to Zn alpha n of this one. The proximal of lambda G of 2xn minus Zn where this is 2, where 2 minus alpha n is plus. So the Douglas-Ashford algorithm for non-smooth cases, for the two non-smooth cases, have been discussed, and that this algorithm, the sequence xn generated by this algorithm weakly converges to the solution of the problem, where the two functions are non-smooth functions. So if we are discussing about the numerical optimization, we can also, well, there are many, but I will try to explain the very classical ones. We have several. The Douglas-Ashford algorithm is also improved. It's also discussed for primal problems. And if we have A of X forms, I mean, many algorithms are there. We can also have, I have results on this one. If we have H1, H2 are two real Hilbert spaces. If we have in H1, if we have H2 in this space, where G is from H2 to R, and F is from H1 and G is and if we have an operator A, boundary linear operator from H1, H2. So find a point in this space which minimizes this one, and under linear transformation A, it also minimizes this. So this was discussed, I think, in 2016 by Modafi, from Professor Modafi in France. I have also research work on this kind of problems. Maybe this is my discussion will be if we have n optimization problems here, and if we have n optimization problems here, and if we have n linear operators. So find the point in the intersection of the point which minimizes all these points, single point, which is an element of the intersection of the minimizer points under any k number of linear transformations. Its image is also a minimizer of this one. We can also discuss this one using proximal operator. Thank you so much.
Questions from the audience?